In this lecture, I want to go over one of the really important things about structural engineering, and that's what we'd call engineering and communication. And I'm using this as a catch-all term for, calculations and how to read and produce engineering drawings and what specifications are. And it's communication because this is really, what the industry is all about and what the profession is all about. It's communicating how to build, so what to build and how to build it. And that's your job as a structural engineer, is to communicate that to a client, to architects, to contractors, to other engineering disciplines who you have to coordinate with. And we use basically these three main tools to do that are going to be calculations, drawings, and specifications. So what we're going to do in this lecture is sort of step through what the pieces are for each of those and how to do them in a meaningful way that's going to be helpful for communicating your design intent to others. So the first thing that we want to look at are calculations, and where you are in your engineering career already. This is all you've done so far is calculations. And you might see this as the calculations you've done are being around statics, and some shear and bending moment diagrams. But why do we do that? Is this just because we're there to make you learn these analytical techniques, which will at some point get replaced by a computer for some which you just need to know and have an intuitive grasp on? So no, it's not just to get you to have this practice doing these calculations. So whether you're doing calculations by hand, you're using a spreadsheet, or you're using computer analysis, they all have the same basic purpose, and that's to communicate your designs and the design methodology you have used to another engineer. So this might be an engineer who is a peer reviewer. This might be someone who is approving your design. So this might be a senior within your own company. This might be someone, another engineering teammate that you have. It might be someone at a building agency, so a city council who would approve your design. Or that other engineer might just be you at a future date, where you want to be able to go back through, and when you might submit a package of work, and then it might be 2-3 months later, you've forgotten all of the fine details of how you came to some of those conclusions. So you want to be able to go back and look at these calculations in order to sort of refresh your memory. And all calculations have a few things. So one, they'll have a table of contents. So this will be the first page or two, which just outlines what the calculation package is. So you might have a set which will be the loads that you have for your building. You might have another one where you're doing beam design or frame design, and then you might have yet another sort of subsection where you're designing connections. And so that's what will be sort of shown and outlined in your table of contents. And then each calculation page has a heading, and that heading has some sort of key information about the firm that's doing it, the designer, when this was done, and sort of what you are actually calculating. And then you have the calculations yourself, and you've got the references. And then finally the last bullet point I have there is any information that might make the calculations clear. And so I'll show you some examples of what that might be. So first thing I want to do is just show you some examples of some calculation sheets. So these are what we've done here at the university for some different projects, some different course projects. A few things to note from them. So you can see that they are typically on grid paper, and that's because we like to do sketches and the like, and so having a grid, one, it provides a convenient scale, and then two, it's a nice sort of guideline for being able to draw straight and orthogonal lines. The other information you'll notice is up here in the heading. So as I said, it's got University of Auckland logo, so that is the firm in quotes that you would be working for your class projects. It has the project that's actually getting worked on. So you can see we've got two different projects here, one for one course that's on the far left, and then the two on the far right as it's a different course around steel design. A description of what the calculation is, and then this description is typically your major heading in your table of contents, who the designer is, what the date is, and then a page number, and then a page. Is it? So I've on the far left, I've done this for section 1. This is page 1 of 10, and the 2 on the right, and here it's in section B, and I've got B 1 of 12 in the middle, and B 6 of 12 on the far right. So the next thing that we would have, again, this is really in an organizational bit, and keep in mind that these calculations are mainly a communications tool. The next thing that we have is sort of a section title. So like, what are the calculations actually calculating? So that if you had to go back through, or someone else had to go through your calcs, they would know that, say on the far left image here, that it's a tributary area of the joints. Or in the middle here, they're sizing a typical secondary beam. Or on the far right, the sizing a primary beam. So it's really clear what the calculation which is getting presented is all about. Following on from that, again, to help make it clear what you're working on, adding in some sketches. So this is that sort of information which might make things, clear to another engineer. And to yourself, things like free body diagrams or bending moment diagrams are really important for being able to really understand the calcs that you have and make sure that you haven't made any mistakes. You might have sketches around the details that you're working on and those type of things. Again, these are just one more way to help make your calculations clearer and easier to read. Another thing that you'll notice on these calcs is that all of the calculations themselves are really well spaced out, and then I'm trying to box sort of these key answers that I need as I go through. And then finally, you'll see that I've got this column here on the right, and what is that used for? So this is most calculation sheets will have this with the the grid lines, and I'll say just one sort of small aside is that calculation sheets are typically never printed front and back, and that's to make them readable. We only print on the one side. But this column here on the right that we have is typically used in one of two ways. So for the image on the far left, I have key answers, and so this might be, I'm trying to find the tributary area on this page of calculations which I'm showing. So when I have that tributary area, and while I've, as showed you in the preceding slide, I've boxed my answer and what that tributary area is within the calculations, I might write it in this right-hand column just to make it really clear and really easy to reference back. The other alternative, and what I have on the two images on the right, in the middle and on the right, is a references column. So we use references for when we are calling up, equations from design standards, or we're calling loads from previous pages. So in the middle image, you can see, I've got the reference of page A3 for both the bending moment and the shear force, which is going on to that load. And then just below that, you can see I've got a reference to NZS 3404. Similarly, too, all the way over to the right, I've got a reference of page B4 and B5 for what the moment demands are on this primary beam that is getting designed. And then I have this definition of restraint type, which is coming out of this Harrow report. And so those references are really key, and so that, one, where you've pulled things out of, and then two, so that another engineer knows that you're not just generating these design equations and these design recommendations arbitrarily, and that they are coming from something like a design standard which has been vetted quite thoroughly and sort of agreed upon by the profession as the way that we should approach this. So that's an overview of calculations. I think maybe just one final thing to note on this is you'll see that I've done my calculations in pencil, and this is strongly encouraged to do it in pencil or a erasable ink, because with calculations you'll often have to go through and iterate multiple times. And so if you make a mistake, because we want our calcs nice and clean. We want to be able to erase that mistake, fix it, and put it in. Similarly, too, you might find that you made an error when you're doing one calculation and that has carried through. And so the general calculations are fine, but you might need to change the numbers here or there. And the last thing I'll show on these calculations is, while I've shown you hand-drawn calculations, which is a sort of tried and true method, more often these days you're going to use calculations, some combination of hand calculations, spreadsheets, and computer analysis. And we will talk a little bit more about how to present those later on in the course. But the key thing to remember is that all of these rules still apply, whether you're doing hand analysis or you're using a computer to help you do this analysis techniques. And that when you are presenting printouts of computer models or spreadsheets, you still need to be able to walk through an engineer that is not you at the present day, how you came up with the values that you have, what your inputs were, so that it's very clear and it's would be reproducible by another engineer. If you're giving them this material, they could tell exactly what you've done for your design. So that's calculations. That's our first set of communication tools that we will use and that we are expected to deliver as a structural engineer. The next set, and arguably probably the most heavily used set, are the drawings. And so drawings are really our way to communicate the design intent. And this could be to, again, another engineer, so like a peer reviewer or someone within the same firm that you are working with. Oftentimes, to the client, and that client might be a private individual. It might be a private entity who, this might be like a development firm, or it may be a institutional owner. So perhaps you are working on a bridge, and so you would be going to the territorial authority who owns that bridge. So in New Zealand, that would be NZTA. And so you need to be able to show them, well, this is what we're proposing to get built and what we've designed. And, your drawings are going to take what you have calculated in your calculations and then turn them into a set of instructions which can get built on site. And there's a number of different types of drawings at the design stage. So you've got architectural drawings, which, as the name suggests, are going to be produced by the architect. And these are going to show things like the general layout of the building, sometimes the furnishings, sometimes, a bit of where the facilities are. And it's really to help give an overall shape of what's going on with the building. Oftentimes, architectural drawings will also include things like the building envelope. So this is the cladding system, so the windows and the walls, which keep the weather out and make the building and separate the buildings indoors from the outdoors. Another set of drawings, which is sometimes included in the architectural set, are what we call the MEP drawings, the mechanical, electrical, and plumbing. So the mechanical drawings, this will be your what's called your HVAC system, so your air conditioning systems, your ability to move air throughout the building, as well as, if you've got elevators and the like. Your electrical is as it is described. This is how your lighting is distributed, how your power points are distributed around the building. And same thing too with the plumbing of, how are you getting pipes of, both clean water and wastewater into and around and out of the building. And then sort of the final set we have, which we're going to focus on here, is the structural drawings. So this is where, this is our product as a structural engineer, is, how do you build the structure? How do you build the bones of the building? And that's design drawings. Now there's another subset which I have down here is fabrication drawings, which we won't get into today. We will talk about more as you go through your career. But this is essentially a set of drawings which is sitting in conjunction with the structural drawings, so if the structural drawings give you the overview and the details of, what might need to be built, shop drawings are what, particularly for steel construction, it will be the, if you have a beam that comes in and it has holes in the end and it's got stiffeners in it. That's a lot of information to try to put onto a structural drawing, which gives an overview. So sometimes shop drawings will be what is used for sort of an offsite facility, so a fabrication workshop or a precast factory, to build the components, which will then come up on site, and then the structural design drawings will show how those components go together. And so those, and as a structural engineer, you will need to review shop drawings as well, because to make sure that the institution or the outfit who is doing the fabrication has interpreted your design drawings correctly and that everything will fit together. So that's the type of drawings that we have. Let's have much like with calculations, let's have a look at, what makes up a drawing, what makes a good drawing. So we'll just give you an overview, a sheet list here, and just to sort of highlight some of the key things. And one of the big ones is that every drawing has a title block. And it's this area here on the right. Some drawings will have the title block along the bottom. Both are fine, and it's really it depends upon the firm who is doing the design. The reason that title blocks tend to go on the right is because the drawings will get bound as a set on the left, and so you can easily flick through and see what the drawing sets are, and then open up the drawing. So it's kind of like having page numbers on the bottom of a book. The next thing that is sort of within the title block will be some information about the job. So the designers who job this is and who built it, who what the project is, and sometimes that is what the client is. So you can see for this drawing, this is the new engineering building that was built in the sort of around 2019, 2020. It opened up. So it's a University of Auckland job. And then you can see that it has a job number down there, and that job number will be within the filing system of the design firm, so that they can go back and refer to, instead of it's like, is this the building 405 job? Well, there might be a number of different designs or smaller jobs associated with one site, and so it's useful to break those up into individual job numbers. The next thing that's sort of in with the title block is you're going to have a sheet title. So what is this one telling? It's a descriptor of what is on the drawing, and along with that, a sheet number. And as you can see, this sheet title is the structural drawing list. It's got a sheet number, and if you can see over in these columns, you'll see there's a number of different numbers which will correspond to these different drawing titles. This one happens to be within the title block, but if your title block goes horizontally, it'll just be up in the upper right-hand corner. These will be sheet notes, and so these are specific call-outs or instructions about what is in the drawing. So they might be some specifications on the type of material that you're using. It might be a certain clearance which is needed. And so anytime you see notes, always go up and have a look and make sure that those don't get forgotten. The other important thing, which is in title blocks, is the revision history and sort of the current revision that you're on. So because drawings will go through a number of iterations for when they go for approval, for consent to get built, and for construction, and then after the building's built, there's often a set of as-built drawings. And so it's important to know, where you are and what's had to get updated in these drawings, because they're a record of what got built and what was intended to be built. And you'll see within the revision history there'll be a descriptor of what this revision was, whether it was for consent, and then maybe in this consenting process when things are getting approved by the council or the peer reviewer, then things had to get changed, and so we want to capture what's been changed. And so with that change, and often you'll see changes in a drawing sort of highlighted with what looks like a cartoon of a cloud, some squiggly lines moving around to indicate, this is new to this set of drawings. But you'll see what that change is, and if the drawings have needed to be revised, and what that revision history is along there. So moving on, so some types of drawings which you will get will be, oftentimes these drawings come in these great big sets, and often it's nice to have a cover sheet. And so, again, this is the Building 405 drawing. More and more these days, as on the cover sheet is a three-dimensional rendering of the building or the structure which is getting designed. One, it just provides a nice overview for the client or the engineer to know, yeah, this is what we're going to be looking at, and as well as it can provide sort of a high-level list of what is in this drawing set. And so you can see that, there on the right, there are some general notes, there's some floor plans, some elevations and sections, some detailing, and all of these separate sections. Moving on from there, we've already seen this image, but this is essentially a drawing list, so it's a table of contents with large. So for smaller construction projects, you might not need this as much because you might only have a set of, say, 5, 10, 15 drawings. But when you get into these very large projects, you might have tens of drawings. You go up to 100 different separate drawings. So it's really kind of necessary to have an overview so that you can navigate between the two. Between two different drawings and around different sections so that you can get the information that you need. And this is you as a designer who might be reviewing these drawings, but really important for those people who are going to be constructing this. And you can see on this drawing list that it also has some key some key information here. So it's got the revision letter, so whether A being the first revision, there's a few D's, there's a few E's there, so some of these drawings have needed multiple revisions, and then it also has, for what was the current issue, so it's this set of drawings is what has been issued for construction. It would be expected there would be yet another set of drawings which would be as built, so after the building has been constructed, just to confirm that what was specified actually got in the same place as intended. And then, almost every set of drawings will have, after a table of contents, a big sheet of general notes. And so I haven't shown you another big sheet of text because it would be kind of boring, but we're going to just sort of dive into some of the things which are on these general notes. And they're going to provide really overarching and common information for which applies to sort of the whole building or the entire drawing set. So what we have here are the building code or the design standard that has been utilized for the design of this building, as well as what the assumed gravity loads are for the roof or the these different floors. And then what the snow, wind, and seismic loadings are. And again, it's a nice quick snapshot of how was this building designed and what were the assumptions which were made. Continue on to general notes. As I said, split this out into your different loadings, and so for design loadings, your gravity and your wind loads. And then we'll start to go with some specific requirements for different materials. So almost every building has some concrete in it. It's almost so most foundations are typically concrete. There are some which are purely timber, purely steel, but many buildings utilize concrete at some stage within the construction. And so we need some overall important notes about how we're going to use concrete in this building. And this is maybe a good time to say that a lot of these general notes are common from job to job. And so you'll see them getting recycled from one set of drawings to another because most of how we build things has been standardized. For how we place concrete on a job site, it's quite standardized, and we just need to make sure that it's there. But it is important to know that if you, as a new engineer, are going to come across this, you want to make sure you're not just blindly copying general notes which refer to one job onto a job in which they're not applicable. So for the concrete, some things which you would expect to have out are going to be, the materials and construction standards used for the design. Now, these are going to be different than the design standards. So your design standards are typically around determining a loading onto a material. while your construction and your material standards will give specifications for how you can place the material on site, what tolerances you have, and that type of thing. Other things which are important are curing. So, how do we make sure that the concrete is cured correctly so that it doesn't dry out, so that it doesn't get too wet, and so that it comes up to proper strength. Other things are around like concrete cover and mix requirements. And so around those two on cover and mix requirements, with mix requirements, you can see that we've got over here in the image on the right, we're going to specify the F prime C, which is the strength that the concrete cylinders would come up to after 28 days. And, keep in mind that the higher strength concrete we have, the more cement equals, the higher the cost. But then you'll see other things about the mix. So like how big the stone, so the aggregate, can be inside, how much slump can be for the mix for these different structural elements, for whether it's a foundation or it's the topping on a floor or it's the precast concrete panels. And that slump is a measure of how much the material flows. And you'll learn more about this in the coming semester when you take your materials course and you look about concrete in detail. Similarly on cover, so cover, we don't just allow the reinforcing in the steel to poke out. We need to make sure that it has some minimum amount of concrete around that, and that helps with durability to keep the reinforcement from rusting, and it also keeps it from getting too hot and melting and losing strength during a fire. And that information is also going to be there in your general notes. Keeping on the concrete theme, so we rarely ever have just a big chunk of concrete with no reinforcing steel in it, so we need to provide some overview and some general information about what the reinforcing steel looks like. So one of the things we care most about is what the grade is, and by grade of reinforcing steel or grade of structural steel, what I'm referring to there is what is its strength. So at what stress does it yield? And that is well defined within material standards, and that's we care about that and making sure that that's on the drawings, because that's the exact thing that we've utilized and designed to make sure that our structure is going to be able to withstand the loads which are going to be imposed upon it. Also, which is important are some typical details. So we don't want to have to be drawing these at every time we draw a section or a detail on the design drawings, and so we want to make sure we hook our reinforcement to make sure that it's anchored and it doesn't pull out. But those hooks are standard, and so we just want to make sure we have those in one place at the beginning of the drawing. And then the last thing there is these drawing keys. So if you look at the image on the right, you can see on point number 1, bars shown with a solid line indicate that reinforcement which is on the top of a beam, and that bars with a dashed line are going to be reinforcement at the bottom of the beam. And so this feels like it's a little bit buried within this set of general notes, but these are things that I kind of want to highlight for you so that you can, if you as you're going through a set of drawings, like, well, why is this looks one way, and I've got these lines down the bottom. What's the difference here? Well, now just go back to the general note sheet, and that will sort of help give you some indication of what you should expect in terms of the what these different symbols mean. Continuing on with general notes, so for structural steel, just like with reinforced concrete, there's the general notes have a very similar feeling. This is material standards, some places where, because steel comes at finite lengths, where we can splice it together and where that's allowable, where it's not. Some fabrication requirements. As you can see, the shop drawing requirements down at the bottom. It says, if you're going to have structural steel work, the design engineer has to sign off on the shop drawings before you can start putting that structural steel into the building. And just like with concrete, there will be some standard connections which will just be on the general note sheet. Sort of the final thing that I want to touch on with the general notes are around bracing and construction. So this is something around the distribution of engineering labor. Typically, the engineer who has designed the building is not responsible for designing how to construct the building. So that will fall under the responsibility of the construction contractor, and they oftentimes will either have their own in-house engineering team, or they will engage a specific temporary works engineer. And that temporary works engineer will design the bracing, any formwork, making sure that the structure can get designed, can get constructed safely, instead of and make sure that the temporary works, which will get removed before the building is completed, can withstand the construction loads, and make sure that everyone's there safely, and so that the building gets built without any hiccups. So moving on to structural drawings and the actual drawing part, what most people think of when they think of drawings, they think of building plans or the blueprints. And so I figure we'd just give an overview definition of what is when we refer to a building plan, what do we mean? And what it is pretend that you're standing on the floor of a building, and you've cut the building all the way parallel to the floor at 1 meter above it, and you're looking straight down. And that's what the building plan is representing. What you can see in this image is if you have a dashed line, that's what we call a hidden line. That means that these dashed lines represent an element which is below the floor, which would be just out of sight. But it's important. So for how the structure behaves and how we would read the drawing, so we want to make sure that we include it on here. A solid line is obviously something that we have cut through and that we can see. And then you'll notice that we've got dimensions in these other call-out lines, which are a thinner line weight so that they aren't as sort of visually stimulating, because what we want to make sure is that the structure, it has the heaviest line weights and the thing that is easiest to see for us, because it's the most important part of the drawing. Now, all structural drawings will have grids and have grid lines, and so what these are a way to sort of locate yourself within the building. So instead of saying, I want to talk about the column, which is, 3 columns over, 2 columns to the north, it becomes really confusing really quickly. It's a lot easier to say, what about the column at DT1 and D5? So you know exactly, I've got a grid line DT1, and then I go over till I hit my grid line D5. And so it's a coordinate system for the drawing. And it is typically defined by the architect, because the architect is the one who is setting the overall shape and form of the structure. And they will often be located along major framing lines of structural elements. The conventions which are typically used is that in one direction, grid lines will be, have numbers. So they'll be like grid line 1, grid line 2, grid line 3. And then in the orthogonal direction, they will have letters. So it'd be grid line A, B, C, D. And we try to avoid letters I and numbers 0, because it's really easy to confuse a letter I for a number 1 and a number 0 for a letter O. And then the last sort of point I have here is that you'll sometimes see elements which are not on a major grid line referred to with this sort of decimal point notation. So if you look at the upper right of the figure here, you see that there's a wall which is running sort of it's running parallel to grid lines DU1 and DT1, but it's not actually on a grid line. So if I want to talk about this wall, I'd say, that'd be the grid line. That's the wall which is on grid line DT 1.6. And so it's about, 60% of the way between DT1 and DU1. And so that's just another thing that you might see and just want to become a confusion. All right, so from plans, then we'll move on to sections. And sections are, one of the are really, really important aspects of drawings, because it shows in greater detail, how these connections work and how a building is put together. And there's a really clever convention for, if you've got a plan, and you'll see this call out, which is this circle with a little triangle on top. Little triangle is indicating which way you would be looking, and it will reference to the item number and on the drawing sheet which the section is located. So on the left, you can see that, all right, we're looking up at this foundation footing. So we're looking up and to the right, and it is going to be drawing number 16 on page 3.5. And so if we jumped over to the image on the right, this would be drawing page 3.5. You can see number 16 is what's circled, and then it references back that, this is, you would see this section on plan on page 2D1. And so you can just jump back and forth and back and forth. So, and now just a real brief run through of some of the, other, typical ways that we, in sort of shorthands, which are used for, noting drawings. So we've got footings. So footings are, how we support the foundation and support columns. Often you'll see them drawn this way, where they only have reinforcing steel on the bottom. But because we have lots of footings in a building, we often don't want to, put down each and every footing. So instead, we'll write up a what's called a footing schedule. So if you see a footing schedule or a column schedule or a beam schedule, it's essentially a shorthand so that we don't have to put dimensions and reinforcement on each and every location where we see this. And so what we have here is footing D3, and you can see it's got a hexagon, and then on the plan you can see a hexagon. Well, it says that that footing is 2.4 by 2.4 meters wide by 600 millimeters deep, and it's a pad footing, and it has reinforcement of 12 20 millimeter diameter bars on the bottom of the footing, and that's 12 are going in each direction. And so as you can see, that's a little weird when you first see them, but they're quite a clever way of sort of condensing the information and making the drawing not cluttered. Similarly with column schedule, so it's the same location on the plan where previously we were looking at footing D3. Now we're looking at column DC3, and it's going to show the major information which we need out of the column. So such things like what the size of the column is, so whether it's going to be a 400 by 400, what the longitudinal reinforcement, so the bars which run along the length of the column. So this has 8 25 millimeter bars vertically, so you can see the V, and then it has 10 millimeter hoops, stirrups, or ties, so you can see the little sketch of what the tie arrangement, which are going to be going sort of parallel to the ground, so they're orthogonal to the bars which run along the length. So this is our transverse reinforcement, and it will say, we have those every 400 millimeters. And then it also provides some details around the hooks and where lap splices are going to occur along the height of the building. So some final thoughts on drawings is that to do them well does take a huge amount of time, but the better your drawings are, the less likely you are to run into problems on site. So they're one of those things where it's much like calculations. It's really worth putting in the effort up front, and it saves you a lot of headaches later. And then again, ultimately, these are one of the main deliverable tools, and one of the things that you'll spend a lot of time on as a structural engineer. So we get you sort of trained on how to do calculations when you go through university, but a lot of what your job is reviewing drawings. And just remember, they're a communication tool. So our final of the 3 sort of modes of communicating our design intent with clients and with those who are going to build a building are specifications. And so you can think about specifications as sort of like the more intense version of general notes. So this is the exact way, how are you going to build everything that I'm saying in the building. So what materials are you going to use? What product type are you going to use? So for example, you might have specified some anchors which you're going to drill in and hold some some fixing on. So maybe you're holding some precast panels on. So you say you should use anchor from manufacturer A. And so if the contractor says, well, actually, manufacturer B, it looks very similar. We already have a bunch of those. Can we use them? They have to, by law, ask you before they swap that out, because you've specified a particular product, and that particular product might have, behavior and the ability to, withstand larger deformation, which another product might not. Conversely, you might have products which are easily interchangeable, and it's just a simple, yes, you can go ahead and change it. But again, because the specifications exist, that's why that they have to check before they change anything. And then similarly, too, sort of with construction methodology, this is particularly true for structural steel, where you'll need specific welding processes to make sure that your welds are going to withstand what you're going to ask of them. And oftentimes these specifications will refer back to those material or construction standards which we referred to previously. So, and just wrapping up, I want to reiterate that just like good set of drawings, good calcs, and good specifications do take a lot of time, but that effort is worth it, and it's really worth it. One, on just making the job go smoother and easier. So, as a structural engineer, your job is to, one, make sure that your structure is going to perform in a safe manner, and that, two, that you have worked well enough with your design to ensure that your structure is going to get built in a relatively straightforward and easy fashion. You don't want to have to come up with a design which is going to be difficult to construct, and that's going to cost more money, cost your client more money, and will mean that you're less likely to get the job in the future. And then sort of the last point here is that, if you do a good job on your drawings, your calcs, your specifications, and you are critical with yourself on how you organize them and archive them, that becomes a very important aspect in case something goes wrong. So something can go wrong on site, such as it could be as simple as before you're going to inspect a reinforcing cage for a pour, and before the pour happens, you notice that, oh wait, we have reinforcing steel which is in the wrong location. So if you got good drawings, you can easily get them out, and you can show the contractor that, no, these are in the wrong location, we need to fix this before we pour something. Or say that you have an element where maybe there was a fire in the building, or there was a collapse, and then you need to prove whether what has caused that collapse, and these set of documents are really important on being able to determine what has caused this issue. Was it inherent to the design? Who is at fault? How do you is it a bigger problem which is across multiple structures, which we now then need to open an investigation and make sure that those are safe so that no one gets hurt? And sort of along with that thought process is just remember that these are a legal document. They can be brought up in court, and so you want to make sure that if you have something which may be potential evidence, that it is in a manner which is easy to interpret and easy to make sure that what you have is correct. So just sort of a brief overview there of sort of these key aspects to engineering communication. We're going to spend some time getting you reading drawings and producing some calculations at a very basic level in this course, just to start to get you some practice. But these are some skills which you will develop throughout your career as a structural engineer. So with that, I want to say thanks for watching.